We are taking the liberty to record this session for the purpose of sort of documentation, but in case you would like to not be recorded or kind of not be quoted in the summary document that we have, do please indicate that in the chat below, and we'll sort of make those accommodations. I see that there is actually, in fact, no AI note taker thus far, but in case any of you do hope to bring one in to take some notes, just do please take consent from the rest of the room, because the AI note taker sort of takes down everything said verbatim, and just check before someone anything that they said is taken down. To save bandwidth on the call, please do turn off your camera unless you're speaking. And of course, your mic unless you're speaking as well. Also, all of us are pretty well versed in speaking in Hindi or English, so please feel free to communicate in whichever language you're most comfortable with. We always sort of organize these sessions to have ample time towards the end for questions and discussions, so please do hold on to your questions till the end. But of course, do use the chat box in case there's something immediately you'd like to respond to, or something props up a thought or a question. Feel free to kind of use the chat function as well. Next slide, please, Johan. Great. So just a quick look at the agenda. We have about 5 minutes of kind of context setting, as well as me just briefly introducing Raghu, who will kind of be leading the presentation from the Wadhwani AI team. Then I'll hand it over to Raghu and his team, who will walk us through sort of their project and the work that they've been doing. And as promised, we have about 30 minutes for questions and discussions at the end. Right, just because I noticed that there are quite a few new people who've joined the coffee hour session today, we just wanted to kind of give a quick check-in about the CoreNet community. Thus far, we have about 55 member organizations working across 23 geographies across the country. We have more than 200 individual members on the Slack workspace, and we're constantly sort of sharing resources, events, and having discussions. We also have we've reached the 80 number mark of submitted projects on the CoreNet web platform. So if you are curious to kind of check out the new projects that have been onboarded, please do check out corenet.in. And of course, update your existing studies and upload new ones, and feel free to connect us to any researcher or research organization for whom you think CoreNet would be a useful resource or a community to be a part of. Next slide, please, Rohan. Right, and I thought this would be maybe a great small plugin. We could let everybody know as well that in April, we're hoping to have the CoreNet conference. We're working towards organizing a conference, which will be 4 days of learning and exchange amongst different organizations within the community. We're hoping to have workshops, plenary sessions, sort of roundtables, speed networking, and of course, a few interesting performances to sort of as a break between sessions. So if there's anything you'd like to share with us, or you'd like to be part of these conversations are sort of ongoing in parallel. So do reach out to us if you have any ideas or thoughts, or you'd like to be involved. We'd be happy to kind of steer those conversations with each of the organizations or members. Right, and this is just a quick map to show you, I guess, the road up to the conference, where today we're at the 25th of February, where we have our coffee hour session with Wadhwani AI. The next coffee hour session is organized for the 11th of March, which is with the Yapti Institute. And then following that, we're trying to organize what we're calling a conference curtain raiser, which is on the 25th of March, which sort of marks the anniversary of, I guess, the lockdown, and kind of having that be a real a stone setting as we work towards the conference. Right, and just to kind of give everybody a little bit of context about what these coffee hour sessions actually are, they're scheduled to be sort of monthly sessions on Thursdays between 4 to 5 for all CoreNet members to convene and informally discuss, share, and learn from each other's work. We do try and emphasize that all these sessions are co-created. So if any member organization wishes to share their studies, or have a conversation about something new and interesting, please do feel free to reach out to us at the email ID provided, which is hello@corenet.in, to discuss a session you'd like to host or propose, and we definitely try to incorporate that as we move ahead. Right, and without further ado, I think I'd like to hand it over to Raghu from the Wadhwani AI team. And just like a quick introduction, over the last 2 decades at the intersection of technology and social impact, Raghu has developed, launched, and scaled innovations in AI, medical technologies, rural energy, and transportation. As a part of the founding leadership team, He helped build Wadhwani AI into a globally unique organization developing AI-based solutions in tuberculosis, maternal and child health, COVID-19, and cotton farming. He's also an alumni of Cornell, UMass Amherst, and IIT Madras. So with that, Raghu, I'll hand it over to you to please walk us through the really, really interesting work that you and your team have been doing.
Thank you. Thank you so much. Keshav, over to you so that you can present. And even as we pull this up, I'll just say there have been many leaders in this effort. It's been a privilege to be one of them in leading a team of more than 30 people, both in Wadhwani AI and beyond, especially the data science volunteer group that has joined forces with us in this effort. Let's move, Keshav. Next slide. Next. Yeah, so the journey really started with in March and April, there was an outpouring interest from a variety of organizations to collaborate to really serve what was a moment of crisis. Right. And next slide. Yeah, and we started out with the thought of building a toolkit that we then will use to serve multiple cities through our partner network, especially through the Smart Cities Commission. However, as we rolled into May, next, Keshav, as we rolled into May, it was pretty obvious that what we needed was a full service approach. And when we say full service approach, it involved us working very closely with top decision makers, having war room presence, so that we understand the needs, the data, and the context. And we had a pretty large team doing modeling and analytics, but also a large part of this team actually doing research in parallel to address the specific needs. And in the process, we have developed some pretty novel techniques that our researchers will share today. But the key, of course, was ultimately having actionable recommendations. And we took the same approach later on to Jharkhand. Next, Keshav. As you can imagine, this, what we hope will be a once in a lifetime effort, had a lot of challenges. The needs were always evolving. The stakeholders, decision makers, and even a large cadre of officers supporting them did not understand epi modeling or analytics. And as a result, their expectations around time horizons for various projections and the accuracy expectations were frankly unrealistic, right? And at the same time, you could imagine, you probably all know there are a lot of data challenges. And as if on cue, my neighbor upstairs starts drilling. Sorry about that. But one key thing I do want to mention at the base of all this was really building trust and confidence in our recommendations. And we addressed this using a combination of both choices on both the technical, non-technical front in our approach, as well as the specific technical approach we have taken, right? We worked directly with top decision makers. We had war room presence. We set up an on-call process so that we could be responsive. And we really delivered recommendations in a way that actually helped them take actions as soon as possible. And of course, at the core of the technical effort, it had to start with actually helping them clean up data and building data pipelines. You will hear later on from our researchers about the novel machine learning approaches we came up with for parameter fitting, as well as uncertainty estimation, so that we actually help decision makers choose the right planning scenarios. And responding to their needs, we had to go well beyond modeling and do various types of analytics to actually be effective in the war room. So with that, let me hand over to Keshav.
Thanks, Raghu. So broadly, as Raghu said, the core of our work was really in using epi models. But broadly, in terms of the decisions that were driven, they changed quite a bit over the course of the pandemic. So in early March, as cases were rising, an immediate need was medical capacity planning. So having forecasts in the range of 30 to 45 days, which is really a horizon within which cities can act. capacity, ramp up capacity was critical. And beyond that, as testing policies and discharge policies changed, as antigen tests came into the market and started to be rolled out, at various points there was need for modeling various scenarios to plan for potential paths that the pandemic could take. So really at the core of our work was trying to see how models could address capacity planning and scenario modeling needs. But beyond that, I think just as data scientists working in this space, there's just space to do much more in terms of cleaning lineless data, helping tag that towards and get a more granular picture of where case discoveries, even analytics, really became a fairly significant piece as well moving forward. And as Raghu mentioned, this involved a fairly close, working relationship with the war room itself. And the recurring theme that you would see throughout this talk today is really how there are several humans in the loop, right from understanding priorities as they evolve, be it how should we be deploying tests, how much should we be testing, redistributing tests across squads, etc. And constantly understanding the data as well, right? As new data streams are added, backlogs are resolved, etc. And within the forecasting service itself, right? So what you see in the green box is mostly internal. We take about a week or two or we typically took a week or two to actually generate each of these forecasts.
Sorry, we can't hear you too well. Your voice is breaking up for us. I'm wondering if that's happening also for the panelists.
Right.
Anyone else?
Hello, is this better now?
Keshav, your voice is very choppy.
There is basically noise.
Right. I'm just right. Okay. Raghu, do you want to quickly go over the next few slides then?
Yeah, I'll do that, Keshav, if you want me to do that. Yeah, so like Keshav was mentioning, this is so at a high level, we did what you will hear from our researchers are challenges and approaches we've taken on data infrastructure, the type of modeling work did, and also the analytics decision support that we provided. Right? Hello?
Hello, hi Raghu. Sorry, I think even your voice is sort of breaking up a little bit.
Alpan, are you there?
Yes, I'm here.
Okay. Yeah, can you take over from here?
Srujana, yes, go ahead.
Oh, all right, okay. Sorry about the confusion. Just wanted to set this up. I just wanted to get to the forecasting effort. So as Raghu and Keshav already articulated, to mitigate these effects of the pandemic, we need to have a sense of how the future is going to pan out. And in particular, it was critical to predict the number of likely infections along with various stratifications. And again, there are multiple use cases, and these could be used for containment, medical capacity planning, and policy making. And our particular focus was on medical capacity planning. And in particular, we wanted to make very precise recommendations on staffing and provisioning for ventilators, oxygen beds, and so on. So we will all be collectively presenting the details of this effort. And Nayana will be going over the problem formulation, forecasting framework, and some of the data challenges and how we resolve those, as well as the model landscape. And Alpan, who heads data science, is going to, and along with Sansiddh, will be presenting the core of our modeling effort and the main technical innovations from the team. So on to you, Nayana.
Right, moving to the problem formulation. So basically our goal here is to predict case counts for various local regions under different scenarios. So the data we're using consists of time series of case counts of confirmed, active, recovered, and disease cases, And we have this data until the current date, and we want to forecast into the future. So the scenarios here could correspond to a continuation of the status quo, or it could correspond to specific changes in the lockdown restrictions or the testing levels. And the accuracy metric that we're using here is the mean absolute percentage error, that is the MAPE on the case counts. So there are multiple aspects for us to consider. We need to build models and generate forecasts that are contextualized for different regions and for different time periods, because the testing policy, recovery policy, and the conditions on the ground vary a lot for different regions. For example, on the right, you can see case counts for 2 different regions, Pune and Mumbai, and we see how much they vary. And there are also data quality issues which have to be handled, which we'll come to a bit later. So here we're considering these confirmed, active, recovered, and disease cases as shown in the plot. But sometimes we need to stratify these or break these up further by severity, by age, by words, so on. So this points to the importance of a solution that is model agnostic, a model that can handle all of these stratifications and so on. And finally, the accuracy or the fidelity criteria also varies based on the end user. For example, in case of medical preparedness, we needed accurate forecasts for about a month, whereas to decide lockdown policy, an ordering of the scenarios would be more useful. So basically, our solution also has to be loss agnostic. So this is our overall epidemiological forecasting framework. We have 3 main phases here. So the first one is the data operations. So this involved working with government officials to consolidate, clean, and consume the data. So we had these data pipelines with semi-automated quality checks and monitoring, and privacy-preserving data pipelines, scripts to clean up data, and so on. Next, we developed a modeling framework, which had several modules for loading data, for training multiple models, fitting, forecasting, evaluating our models, as well as publishing the forecasts. So the framework was quite extensive. It accommodates multiple models, different loss functions, various types of black box learning, and so on. And the final step is the report generation, where we customize planning reports for war rooms and for decision makers. And as you can see, we have inputs which come in from the city at various points. So we have the planning and horizon criteria. We have upcoming policies and events, which we use for scenario condition forecasting, and the staffing and supplies maps, which are used to translate our forecasts into medical capacity requirements. So as we mentioned, data operations was something which was quite extensive. And this was because there were a lot of data challenges involved, and some of them are listed here. So we had manual entry errors. So at the point of entry, there would be mistakes in the data entered, which required automated validation. We had duplicate cases requiring resolution at the city level, deduplication. There was weekly periodicity in the cases. For example, we would observe that on one particular day of the week, there would be a small spike in cases corresponding to the day on which a lot of testing was done. So this was handled by taking moving averages of the time series. And one of the major issues we faced was spikes due to backlogs. And on the right, you can see an example of this where the data has a huge spike because the recoveries over a month or so would be reported on a single day at the end of the month. And so we would have to back distribute this huge spike in the data across the backlog period in a weighted manner following the distribution pattern, which we thought was most likely. So in order to do this forecasting, there are several different types of epidemiological models which are available. And they broadly fall into these 3 buckets, which are shown on the slide. So the first are curve fitting models. So these are based on learning algorithms that fit to data, but these models are often not interpretable, which is problematic. The second category of models is compartmental models. So in these models, the entire population is divided into different compartments, and people transition from one compartment to the next at some particular rate. So SEIARD models are examples of compartmental models. The benefit of these models is that they're parsimonious and very interpretable, something which was useful for us. The third category, which we've shown here, are agent-based models, which capture behavior at the level of an individual agent. But these models tend to have a lot of parameters, which makes it non-trivial and difficult to calibrate them with real data. So given the practical requirements, the data constraints, and the modeling tenets, our forecasting operations have mostly been focused on compartmental models. And over to Sansiddh to explain our specific model and methodology.
Cool. Thanks, Nayana. So, so as you can see, we use this model, which is sort of, we call it the SEIARD model, which is just a concatenation of the states. This is based on like the SEIR models, which are very popular in the epidemiological world. They work by sort of modeling the flow of once an individual and contracts a disease, the entire flow. They work by modeling that. So initially you start off with we assume the entire population is susceptible, and that comes in the S bucket. And then you start off with an initial set of infected individuals, and there is the infected individuals and the susceptible population, they interact, and then parts of the susceptible population, they become exposed. Now it takes a while for these exposed individuals to become infectious themselves, because the viral load in their body does not increase suddenly. It takes a while for it to increase, and they then become sort of infectious, and they spread the disease. And these folks, they remain infectious for a while, and then they transition to these sort of active states, where they are like, after they have tested, right, they still have the disease in their body, but they are not spreading the disease anymore. So now with a probability p fatal, they transition to the state A fatal, where they end up spending time T fatal trying to fight the disease, and then they sort of unfortunately die. With and with probability 1 minus p fatal, they transition to the A recurve state, where they spend time T recurve trying to fight the disease, and they ultimately become cured. So this is a sort of like a crude approximation of the entire flow of an individual. And for each of these transitions have a corresponding parameter, right? What is p fatal going to be, what is the time to death usually, like what's the time to recovery, etc. And Keshav, next slide. So these parameters, they vary. Keshav, can you go back to the slide before this? Yeah. So these parameters, they vary across regions, they vary across populations group. They completely depend on the policies of that geographical region at that time. So there are like a lot of factors that these parameters depend on. And typically, a lot of the times, these parameters of these models are handcrafted. But what we do is that we learn the parameters of these models using machine learning techniques. And to talk about how exactly we do that, I think I would like to sort of invite Alpan to go ahead.
Hi everyone. Can you hear me? So Sansiddh described the overall structure of the model that we use. I'm going to describe the parameter fitting process. So in this slide, the first equation there essentially describes the forecasting model. You have an initial set of case counts and a time horizon over which you want to do forecasting, and so you get a predicted time series. And the way one typically frames this problem is you choose or you fit epidemiological parameters in a manner so as to minimize a certain loss function. Right. So here the loss function is evaluated between actual counts that you observe and the ones that are predicted. So that this is the typical estimation technique. You minimize an appropriate loss function. Many methods to do this. The one that we use is Bayesian optimization, where you assume a reasonable prior, typically uniform priors on these parameters that come from epidemiological considerations. And then we use a sequential model-based optimization technique to keep improving iteratively improve one's estimate of theta. And in the process, you get various samples of theta until you converge on a near optimal solution. Now, one problem with this method is that these point estimates of theta, these sort of arguments that you get from doing this optimization tend to have high variance. They're not very robust. Plus, they don't sort of naturally yield an uncertainty envelope on the parameters. And uncertainties is not just useful from an academic perspective, but also useful for on the ground predictions, because our customers, in this case, we were mainly serving the city of Mumbai and the state of Jharkhand. They wanted to know sort of forecast ranges on, how many hospital beds they need to plan for and so on. And so we had to describe various scenarios corresponding to different ranges on our forecast. So the way there's a rigorous way to do this using Markov chain Monte Carlo, which I'm not going to describe here. What the method we used was an approximate method that seemed to work quite well. In fact, we did extensive comparisons with MCMC to show that it works well. The approximate method is we constructed a posterior distribution from the SMBO samples. So what we did was we assumed that the posterior distribution is proportional to some e to the minus c times the loss function times the prior, and where c is sort of an unknown parameter that's further estimated through validation on a small holdout set. So we take a few days of data as a holdout set, and we choose c in such a manner that we minimize the expected loss on that validation set. So, and the way we construct the posterior distribution is we create this weighted ensemble of models from multiple trials of the SMBO process. So in other words, this is sort of our weighted ensemble technique. We have a uniform prior, we have theta I are samples from the SMBO process. P of theta I is typically a uniform prior, but doesn't have to be uniform. And then the samples are weighted by e to the minus c times L. And so one gets robust estimates and through Bayesian model averaging. So we call this an approximate Bayesian model averaging technique to estimate parameter uncertainty and consequently forecast uncertainty. So we can, once we have a posterior distribution over the parameters, we can construct posterior distributions over the forecast and compute the corresponding uncertainties. So this is a comparison between our approximate Bayesian model averaging technique and MCMC. So in each case, the observed data is shown as dashed lines. The prediction of our approximate technique is the sort of orange line, orange or yellow, depending on how you see this. And the blue line is the MCMC technique. And you can see the orange and blue lines in most cases agree quite well, except for the active cases where there's a significant divergence later in time between the orange and blue lines. But also in the active cases, the sort of true case count sort of seems to fluctuate between the orange and blue line. And then the other sort of envelopes that you see is a comparison of the 95% credible intervals in both cases. So, this is sort of an application of our method for the city of Mumbai, and we're looking at different phases of the pandemic here, early phase, middle phase, and late phase. Sansiddh, you want to go over these results?
Sure, Alpan. So as you can see, we have presented our results on 3 different phases, and the model was trained on data till on the gray shaded region, and the region beyond that is the testing phase. And as you can see that the dotted lines is our forecast, and the solid line was the ground truth. So as you can see that our forecasts were reasonably were reasonably able to predict the case load well for like a 30 to 45 day time window. And if you look at the table, the absolute bottom right corner, that's where the loss values in MAPE or the errors in MAPE, that is for the corresponding forecasts, are also presented. You can see that in the early phase our errors were slightly higher, but as as in the later phase of the pandemic, our errors became lower and we were forecasting more accurately. We also wanted to compare the performance of our forecasting method with respect to other forecasting method, but most forecasting methods are sort of based out of a lot of the labs are based out of US, and they've been doing their forecasting on US states. So if you look at the table on the right hand side, that is essentially that shows the performance of our model with the aggregate performance of our model with respect to all other models, and the lower the error, the better it is. So I think we're doing good. And then if you look at the figure on the left, that shows the performance of our model on different states. And so this metric that we're using, it's a normalized version of the previous metric that we had shown. And the more green the state is, the better our performance on that state with respect to other models, and the more red the state is, the worse the performance. And I think in the figure we have far more greens than reds. Alpan, Srujana, do you want to cover the sum?
Yeah, I was just thinking that in the interest of time, we could skip this. I just wanted to call out that, besides the technical innovations that Sansiddh and Alpan talked about, which is this model and loss agnostic optimization, we also had these, there was a huge effort in trying to deploy it on field in Mumbai and Jharkhand for medical capacity planning, and in particular, supporting the decision making. I think we could visit the key learnings towards the end. Let's skip this and then come back to it, because we are at 40 minutes already.
Great. Thank you for that session and having everyone sort of chip in. That was right. So since we have about 20 minutes left, I thought we could maybe open it up to the audience and see if there were any questions. I noticed there were a couple of questions in the chat. Maybe we could take those first, and as
we have a few more.
Hello.
We have a few more slides. We'll get through them quickly.
Okay, sure. Okay.
Yeah, so I'll keep it quick. So like Raghu said, when the pandemic started, as an organization and individual, we were ready to do whatever it takes to help the city and the state and the country in its time of need. So we actually, I worked with the BMC war room on ground on behalf of Wadhwani AI, helped set up a war room. And where we honestly played a part is to help policymakers take quick decisions using the data that was being generated on the ground. And once the execution of law enforcement, of mobility, of testing and medical care was done, and the data that was generated out of it, we all shared our observations with the administration so that they could take decisions that would further improve the situation of the city. Keshav, next slide, please. Right. So this is just the pyramid of how things work. We had massive challenges that the city was facing, especially because there were very few people in the government administration who were coming for work, because most were of the vulnerable age of about 50. So Wadhwani AI as an organization and many other volunteering individuals and organizations played the gap of domain experts in helping in whatever way we could, while the essential services and government administration on the ground was doing its work and generating massive amounts of data, which we helped further refine to take better decisions.
I shouldn't take too long here, but I just wanted to mention that, besides all of the forecasting effort, we were also actively trying to nudge the public health officials and the decision makers to adopt a more of a data-driven decision-making framework. And the core idea here was that they should have concrete metrics to capture the state of the pandemic and the operation of the various levers when it comes to medical care or the lockdown policy or testing and so on. And in certain cases, it was important to just observe those metrics, like say infection prevalence, whereas in certain cases, say it was the test reporting delays and so on, there was a need to nudge them and all of their operations towards certain target levels. And what we discovered in our interactions was there were a lot of metrics like this excess death ratio and so on, which were not even being captured. So this was, I don't think we have time to go into detail, but we could just very quickly look at I could mention one or two metrics here on each of these levels that we were trying to get them to capture, the things that they were not already capturing. So I just felt like there were a bunch of metrics which were not even being captured. And so we were trying to get them to, observe these metrics and capture them, and to the extent possible, try to achieve certain targets for those metrics.
So at the start of the pandemic, one of the important use cases that we discovered and was given to us by the administration was to figure out how much bed capacity, how much critical care resources that they need to plan for months in advance. Because in many cities that we saw across the country, existing infrastructure was not enough. And there was a need to build these temporary hospitals called jumbo facilities to rope in the private sector and unlock some of those ICU and oxygen beds. And not limited to that, but also quarantine beds for which we mobilize schools, hotels, and so on and so forth. So what we did with our projection is that 2 months in advance, we were able to tell BMC along with a certainty estimate about what are the numbers and what are the percentages of breakup, what allocation should they do in terms of number of beds to oxygen, ICU, so on and so forth. So of course, challenges like mentioned before, data was a big challenge. And expectation was also a problem because there were times when we were asked to project for 4 or 5 months in advance, which is not possible with these kind of models. Next slide, please.
Okay, so we used the lineless data to have analytics done, and which kind of focused our testing strategy, and we nudged the officials in the way they were doing testing in different areas. And this step typically involved slicing and dicing data to view things from a different perspective. For example, we took a look at the testing volume, the testing trends, the kind of tests that were being done, the positivity rate, and the age group of the people where the positivity rate was higher. So we did this kind of analysis both for Mumbai and for Jharkhand, and we saw that because of the analytics that we had, we increased the testing in the under-tested wards in Mumbai by 27%. This also helped us identify the hotspots, the center of spreads in Ranchi and in other districts. And therefore, based on this analysis, we recommended a focused testing approach based on the location, which was increasing the testing in a particular ward, increasing the number of RT-PCR tests in a particular block. And that kind of helped shape the testing strategy better. The kind of challenges we faced here was typically related to incomplete data. So at certain points, we were not having the right data for the address, for PIN code, which kind of restricted us in doing the analytics properly. And specifically for Jharkhand, we had a challenge of mapping the addresses present in the line list to the blocks and wards correctly. But we kind of use the keyword matching techniques out there to move ahead with the analytics. Keshav, you can move on to the next slide.
Yeah, so I just wanted to share some of the key learnings, and I might not be able to do justice to everything because some of these involve the collaboration with multiple different organizations. So Raghu, Alpan, Janak, please chime in as needed. So one thing that we had to very much keep in mind was that the AI-based solutions by themselves were not, adequate, right? Because there was a lot of moving parts here. In particular, the definitions of the data were changing, and there's a the data itself would have issues and so on. So we had to have these strategic engagements, and it required like a collaboration between the programs teams, like folks on in the city war rooms like Janak and others, as well as folks on the technical side and even from the engineering team. And apart from that, one other thing that we was important for us while we were doing this was that we had to be very conscious of the fact that we wanted these results to be actionable, and we wanted this to be useful in terms of the impact. And so what we had to work to was the way we picked our modeling choices was very deliberate. We had to really prioritize model interpretability and identifiability, because we were not only just giving them forecast, but we were sharing the parameter values. For instance, we were sharing values of the recovery period from the time of detection to the point person recovers. And because the policy was changing, we had to give these estimates and check if this is really matching the policy prescribed by the officials. And a lot of our modeling choices were therefore dictated by this. Even when it came to things like say model fitting, we had to make deliberate choices on the horizon that we would optimize the loss function over, and the way we designed that loss function, and even the insights that we were generating, which were like, not just plain forecast. We actually had to curate few different scenarios, taking into account some secondary information that they would give. For instance, if they were to say that that we are expecting a festival, or some change in the policy, we would incorporate that into our forecast by appropriately adjusting the model parameters, and then using like other secondary sources like mobility information, and whatever has panned out right, like compliance from past and so on. And
yeah, we would adjust the model priors.
Yes.
And then do
and that, yeah, thanks, Alpan. And then the other thing was the uncertainty estimation that Alpan talked about. So we had to curate these scenarios, which were like, a high scenario, which would be the one for which some, folks need to have a plan B, or like have some reserve resources, and then a regular scenario, or the likely scenario for which they would provision, and a low case scenario for reference. So we would use the uncertainty estimates and different percentiles to curate these three scenarios, because like too much information is difficult for them to consume, and then also convert this into very precise staffing estimates, like number of ward boys in CC2 cares, number of ICU doctors, and so on, which folks could consume. And lastly, I think this I think Janak, Raghu, and Keshav would probably can do more justice to this, because this is a whole relationship building. I think relationships, empathy, and responsiveness are like super important, because priorities keep changing on their end, on the city war rooms end, and we need to react to that. And also, we need to understand their constraints, because they might not adopt everything that we suggest, and they might have a different set of requirements.
Here, I'll say a lot of credit to the team that we just didn't simply focus on, we didn't say we'll just do modeling or AI. We actually had to get into, we understood their needs and got into actually aligning their data systems with their ground needs. Simple things like standard schema definitions, etc., had a big impact in themselves, in both enabling our work and also in bringing a little bit more sanity to the city's efforts.
Okay, so in terms of the leave behinds or the work that we're doing right now, is that we're compiling all the resources, the learnings that we've had through this throughout this journey, so that it can be used in the future context, especially in cases where you can use compartmental models. So we are primarily focusing in three areas. One is technical publications, which talk about our model. The other is open sourcing the code base so that it's available for a larger community of researchers, engineers, or academicians who would want to take a look at it and adapt to their particular use case. And third is a playbook, which is collating the learning from the all the other standpoints, the technical stuff, the tools, the learnings we had while we were dealing with the BMC and the Jharkhand government, the learnings we had while setting up the data pipeline, the data cleaning. So we are compiling everything together to be presented in a playbook.
Okay, so let's, it's been quite active on the chat front, but if there are specific questions, we can still take that. I feel, are there any questions on this thread that aren't answered yet? Or Alpan, Srujana, etc., do you want to touch on anything specifically that you feel like you want to bring out?
I think let's take questions if there are any. I know we have a time constraint.
Right. If anyone has questions, feel free to mute yourself and ask the team.
Hi, this is Priya. Can I go, Nitya?
Yes, please, of course, Priya.
Okay. Hi, thanks very much to the AI team. And I'm sorry the initial part was interrupted and you had to speed through it. I think we would have appreciated more time. But we can read the slides carefully. I just want to reconfirm what I heard one of the colleagues say, is that in the end, I mean, there was one bullet there that, something about the AI models not being perfect, and actually there's a lot of human element of decision making and strategic decisions that you're making on an ongoing basis as you're fitting these models. So, and because it's a Bayesian approach, otherwise I'm not going by any theory, but what I am understanding you say is real-time concerns of policymakers, real-time considerations of data, and just kind of understanding what is happening, like reading news and really absorbing intuitively what is happening, is also affecting the decisions you're making around the model. Am I right about this? I'm obviously using my own interpretation here, but I just wanted somebody to confirm this.
Yeah, can take this, and maybe Alpan, you want to chime in?
Sure.
Yeah, and completely agree with the way you articulated it. That's exactly what we had to do. For instance, if we see, this is not just a forecasting, assuming that the scenario would remain as before, right? It's not a status quo situation. Things are evolving on the ground, and the decision makers do have some level of control in shaping how things pan out in terms of like policy changes. So if we, for instance, knew that the recovery policy was going to change, which it did quite a few times, right? It used to be 14 days recovery, and then they made it 10 days, and they would do something else where sometimes they would like change folks, move folks to home quarantine situations rather than have them in CC2. So we needed to adapt our models and forecast to take into account those upcoming changes on the ground. So that was one thing. And sometimes we had to make use of secondary information that we would have, which might not be in the form of case counts. And like Alpan mentioned, incorporate that as priors in how we, do the forecasting.
And so you also wrote that accuracy is then less important than perhaps predicting, being able to generate some real-time information to decision makers.
No, I would say accuracy is important.
Okay.
But the fact that we could give, the fact that we were doing a Bayesian approach and that allowed computing sort of credible intervals around parameters and correspondingly around the focus, that did help. So governments could plan around worst case scenarios, for example. I mean, obviously there are subjective assumptions there. For example, is 95% worst case, or is it 98%, and so on, or is it 80%, right? So there were subjective decisions there, but the fact that we we forecasted uncertainty envelopes around, around our estimates, that really helped, and that's where the subjectivity was applied. But if these, if these uncertainty envelopes were way off in terms of accuracy, I don't think we could have built the level of trust.
Mm-hmm. Thanks a lot.
Any other questions?
I'm not sure if I'm audible, but I'd like to just add to that. Can you hear me?
Yes, Keshav, broken but still.
Okay. No, I just wanted to share a very quick example, right? So there was one particular instance back in July where we actually forecasted far more cases than there were, than there ended up being, right? So accuracy there, our errors were in excess of 10%. However, while interpreting the forecast, we accounted for the fact that there would be under-reporting, right? So the few cases that are reported are more likely to be serious. But our ultimate recommendation is we're not concerned with case numbers, but concerned with the recommendation of how many ICU beds and CCC beds there need to be. And as long as those recommendations were right, accuracy is just a function of how well cases are reported.
Thanks.
Any other questions? Else, turn it over to coordinate.
Right, I see quite a lot of activity going on in the chat session, and I was just
we answered.
If anyone there wants to
most of those questions.
Right. Yes, I just wanted to check with Romit or Sahil in case there's anything you wanted to ask.
No, thanks, Nitya. I think everyone kind of chimed in, and thank you all for your responses. I think Priya's question also kind of touched upon some of this. So I think I'm good.
Great. Okay. Thanks so much, Romit. I'm going to assume the same for Sahil. Okay. Never mind. Thanks so much to the Wadhwani team, and also for kind of having many different people from the entire team kind of chip in and add in sort of their contributions and answer the questions on the chat box as well. So thank you so much. And in case anyone has any other questions that come up slightly later, feel free to kind of reach out to the Wadhwani AI team. I would just request Raghu or Keshav to drop in an email ID in case people want to reach you directly, or they can also route those questions through the coordinates Secretariat. That should also be okay. So that's all for today. I just wanted to kind of put in everyone's notice that the next coffee hour session we have is organized for the 11th March with the Aarti Institute, with Astha Kapoor, who's one of the co-founders of the Aarti Institute, and it's going to talk a little bit about maybe along similar lines about data stewardship and kind of what that is meant, excuse me, in light of COVID-19. So I hope to see you guys at the next coffee hour session, which is on the 11th of March at the same time from 4 to 5. Thank you, everyone, and have a great day.